This is a linked list. The data is stored in nodes, and each node also contains a pointer to the next node. Unlike an array, the data is not stored in a contiguous memory block, so you cannot access, say, the nth node by its index. Instead, you have to traverse the linked list to search for the node you want, and stop traversing if the next node is null, indicating that we've reached the tail. But a problem is encountered when your linked list has a cycle. There is no clear stopping point because the next node is never null. If you were to use the same code as in the previous case, your pointer would keep moving around and around the cycle in an infinite loop, so it can be beneficial to be able to detect a cycle first. One standard way is to keep track of all visited nodes in a set. Each time you visit a node, you first check if it is in the set. If not, add it and move to the next node. If the next node is null, then there is no cycle and we can exit. But if we reach a node that is in the set already, then there must be a cycle because we have seen that node before. So we can return that that node is the start of the cycle. This approach's time complexity is big O of n because for each node we are only performing a constant time lookup in the set. Where we can do better is the space complexity, which is also big O of n. See, the size of the set grows linearly with the size of the linked list. So is there a way to do this with only constant extra space? Floyd's cycle finding algorithm can detect a cycle in a linked list and return the starting point of the cycle in just O1 space. It uses only two pointers, a slow pointer, the tortoise, which traverses the linked list one node at a time, and a fast pointer, the hare, which moves two nodes at a time, so it is traversing twice as fast as the tortoise. Let's look at what the algorithm does now. Firstly, in the case that the linked list has no cycle, the hare will simply reach the tail of the linked list. So in that case, you can stop and return that there is no cycle. But in the case that there is a cycle, the hare will race away from the tortoise, then catch up to it around the cycle part of the linked list. If the hare catches up to the tortoise, as in the two pointers point to the same node, you can say that there is a cycle in the linked list. But how does the algorithm find where the cycle begins? Once the two pointers meet at the meeting point, bring one of them back to the head of the linked list, then step both pointers through one at a time. Amazingly, they will meet at the start of the cycle. Let's look at a larger example. We start both pointers at the head of the linked list. The green pointer, the hare, moves two nodes for every one node that the tortoise moves. As they enter the cycle, the hare catches up to the tortoise and they meet at a shared node, the meeting point. We then bring one back to the head of the linked list, then step both pointers through one at a time until they meet again. Where they meet is the entry point of the cycle. I think the first part of the algorithm, detecting a cycle, is quite intuitive because the hare is moving two nodes at a time, so it will catch up to the tortoise, which is moving only one node at a time around a cycle. But what is less intuitive is the second part of the algorithm, why taking one of the pointers back to the start and stepping them through one node at a time has the two pointers meet at the entry point of the cycle. Let's take a look at why now. Firstly, the meeting point where the two pointers meet is 15. The distance from the head to the start of the cycle we'll label x. The distance from the start of the cycle to the meeting point is y, and the distance from the meeting point back to the start of the cycle is z. Now we want to show that the distances traveled by the two pointers in the second part of the algorithm are equal. The first pointer moves from the head of the linked list to the start of the cycle, a distance of x. The second pointer moves some number of loops, c times l, plus the extra little bit from the meeting point to the entry point of the cycle, z. To go about proving this, let's start with what we know. In the first part of the algorithm, the distance traveled by the fast pointer, df, from the head to the meeting point is equal to 2 times the distance traveled by the slow pointer, ds. This is because the fast pointer is traveling 2 nodes for every 1 node that the slow pointer travels. We'll fill in these distances from the first part of the algorithm. The fast pointer will move from the head of the linked list to the entry point of the cycle, x, plus some number of loops around the cycle, plus the extra part from the start of the cycle to the meeting point, y. The slow pointer will also move in the same fashion to reach the meeting point, but it will complete a different number of loops around the cycle. So we can call the number of loops NF and NS respectively. Next, we can expand the brackets. And note, 2NS is just another constant, so we can call that N. Then we can make X the subject. Now let's factor out the L. Again, NF minus N is just another constant, so let's rename that M. Let's take one L out of this ML group. Remember, L is just the length of the cycle, which is Y plus Z. Now those two Y's cancel out. Finally, M minus 1 is just another constant again, so we can rename it C. And this is what we set out to show, so we are done. Time to code this. List node is our linked list node struct. It contains some data and a pointer to the next node. Now in our function, we want to pass in a pointer to the head of the linked list. If a cycle is present, return a pointer to the node at the start of the cycle. Otherwise, we'll return null pointer, indicating there's no cycle. Now, we need two pointers, the slow one, the tortoise, who moves one node at a time, and the fast one, the hare, who moves two nodes at a time. These both start at the head of the linked list. Part 1 of the algorithm is to actually detect the cycle by moving the tortoise and hare until they meet again. So do, while the tortoise and hare don't point to the same node. So why this do while instead of a regular while loop? Because the hare and tortoise both start at the head of the linked list. So if we put the condition before the loop body, the loop will actually never be entered because this condition is unfulfilled at first. If the hare is ever null or doesn't point to a next node, we can return null pointer. We've reached the end of the list, there's no cycle. Otherwise, step the tortoise one node and step the hare two nodes. If we reach this next part of the code, it means the 2 pointers met, so a cycle has been detected. Now it is time for part 2, finding where the cycle began. We take the tortoise back to the head of the linked list. Then we step the tortoise and hare one node at a time until they meet again. Where they meet is the entry point of the cycle. So return it, and we are done.